give this presentation. I also like to highlight why you've been listening to all these talks since morning about SETI. You might wonder that this is a conference about FRB and why we are talking about SETI. So the reason is Spotlight. So we are very excited with this new backend that's coming online with GMRT, and we are so much looking forward to collaborate with the team to enable Spotlight to do SETI. And that's why we thought this would be a good venue for us to also highlight all the activities that's happening in our field, as well as like what are the latest development happening in, especially with the high data rate that we are currently trying to process and do real-time sort of searches for technosignature. But this is not something new. My goal for this talk would be to highlight one point, and that is that we've been friends for so long. Technosignatures and FRBs and pulsars, all of them go hand in hand. Like any technology development you do to detect FRBs or for pulsars is also similarly applicable for doing technosignature and vice versa. There are a large number of examples that I'm going to give you today, how one of the things that's happened in one area has helped other fields as well. Obviously, I'm not going to go into too much history, but I felt that it would be nice to give you a very short history of this collaboration of technosignature and FRB, because most of you have FRB interests. So you might find it useful that how FRB has helped us do technosignature work. But before I jump in, let's start with at least more or less like 10 years ago, when one of the largest technosignature effort was launched, and that was the Breakthrough Listen program. So this was a program launched in 2015 at the Royal Society, which, we had been given a task to conduct one of the most deepest, one of the most comprehensive search for a technologically advanced life that humanity has ever conducted. So we've been kind of at that task for the last 10 years or so. Let me give you a small background of what exactly we are doing as a part of the Breakthrough Listen project. We are searching for evidence of technology. Vikram gave really nice overview of what are the different kinds of technosignature one can find. We are trying to search for these technosignature across all different kinds of sources. We are looking at a nearest 1 million star. We are looking at our entire galactic plane as well as the galactic center. I'm going to come to the galactic center toward the end. And we are also looking at nearby galaxies. We are using some of the world's largest radio telescope as well as optical telescope. I may be able to talk to you about two of the telescopes that we use quite routinely. Someone was asking what exactly we are searching for. So there are lots of different kinds of things we try to search when you talk about radio technosignature. Obviously, for the rest of my talk, I'm only going to focus on radio technosignature. So what are we searching for when we say we are searching for ETI? So we are specifically sometimes search for these kind of signals. So what you see here, this is frequency, and you see a narrowband signal like this. These are the evidence of technology. No natural sources are known to produce signals like that. We also try and detect pulsating wideband signal. Again, something that nature doesn't do. Like if you have pulsars are broadband, but if you have a signal that is concentrated only for a very limited amount of frequency, but it's also periodically pulsating, we do produce signals like that. For example, radar signals are similar in that nature. So we are also searching for that. In fact, we are using some of the pulsar search technique that been well tested over the last many decades. So for example, we use fast folding algorithm to search for these periodic pulses. But most importantly for this audience, transient broadband signal, we are also searching for them. Obviously, this is the natural dispersion, but then you can also flip the frequency and time, and you can have three different examples of artificially dispersed signal. Now, these are the signals you may or you may not encounter in nature, because most of the natural occurring dispersed signals, they happen because of the interstellar medium. But you can also produce these signals artificially by leakage radiation. I mean, we see that in RFI, some of these signals are kind of seen in interferences that we are also producing by our own technology. So we are also searching for these kind of artificially dispersed pulses. So this is just an example of different kinds of signals that we are searching. And when we talk about especially these FRB-like signals, obviously That's where our collaboration with the FRB community started. In fact, it started with the FRB 121102. I don't need to kind of give it to this audience, but this was obviously one of the very first exciting FRB, which was localized. At that time, something around in 2017, we were building our instrument to do raw baseband voltage recording capabilities. So we had an instrument at the Green Bank telescope, which allowed us to capture 6 gigahertz of simultaneous bandwidth. We have a cluster of 64 compute nodes, which allowed us to store 4 petabytes of data over there, which is a huge amount of compute resources. We were able to ingest something around 750 megabytes a second. These numbers might sound very dwarf compared to what you just heard from Luigi. At the current day technology, we are at least by a factor of 10 more ingestion. This is a 10-year-old system, but still at that time, this was a system that allowed us to capture raw baseband voltages. So what we wanted to do was that we wanted to try out whether the system works and if it's able to kind of process the data in real time and able to store the data. And so one of the obvious sources we felt was 121102. So we targeted and we got really lucky. And rest is history. I guess I think we probably seen this plot before. So we made the first detection of the FRB 121102 at the highest frequency. Highest frequency was selected because it was unexplored. Again, we are in a SETI field, right? We try to kind of break the boundary. We go to parameter space, which has not been explored before. Plus, this source was heavily localized. So with the GBT, given the beam size, it was still possible that you can go to high frequency because you had that kind of positional accuracy. So we observed that, and we got lucky. We got 15 or so burst from this, and a number of paper came out. You're probably all familiar with that. Our collaboration with FRB community didn't end there. We had a number of other examples as well. So as I mentioned, in our field, we also monitor galactic plane. So in one instant, when we were observing the galactic plane, we had a commensal FRB system which was running in the background, and then this FRB popped up. And we got all very excited, and then we followed it up. And again, because we had the raw baseband voltage capability, we stored the raw voltages of this FRB, and that allowed us to do more detailed polarization characteristic. And I think currently there are a number of papers that have come out from FAST as well. When we first detected this FRB, we thought it could be a GPS satellite or a geostationary satellite. But later, I think this FRB has been currently confirmed to be a repeater with FAST and with a very interesting polarization characteristic. Okay, so all of that detection was done using a pipeline that I built almost close to 10 years ago called Spandak, which was pretty basic. It was a wrapper around an already existing pipeline called Heimdall. I think some of you might be familiar with that, which is a GPU accelerated pipeline. All I did is that I built like an ML-based inference on the output that Heimdall was producing. And I also built my own candidate sorter. If any of you have ever worked with Heimdall, you probably are familiar that it will throw out millions of candidates. Not all of them are real. So you need some kind of vetting algorithm to check all the candidate that is coming out from Heimdall. So what we did is that I built a CNN-based classifier, which was looking for these kind of transient signal using the convolution neural network. And the same pipeline, now you may ask this question that when the pipeline is searching for a dispersed pulse like this, can it also be used to search for artificial dispersed pulses? And so we tweaked the pipeline to modify it to search for artificially dispersed pulses. And the way we did that is that instead of changing the pipeline, we changed the data. So the data that was going into the pipeline, if you flip them in time, flip them in frequency, it's in a way you are searching for these kind of flipped dispersed pulses. So we made the pipeline that was kind of used for FRB searching and made it to search for broadband artificial transient pulses as well. This pipeline has been deployed over many, many radio telescopes. They've been used to discover pulse FRBs from many telescopes. We also use it with GMRT for detect FRB at the very low frequency. We also detected with Sardinia radio telescope, again, to detect FRBs at the very low frequencies. So what are the science that we mainly did with the Spandak pipeline? So we carried out a survey of some of the stars. So I mentioned this earlier as a part of the Breakthrough Listen program. We look at a nearby star. So this is our obviously Milky Way galaxy. The green circle are the sample of sort of nearby stars that we surveyed. And we also looked at directly towards the galactic center. What this plot shows, obviously we didn't detect anything, otherwise I would have been giving a different kind of talk, but we were able to place a very meaningful constraint on existence of these kind of signals. This is kind of like a luminosity function. So this is the output power of any kind of transmitter that you are able to detect. And this is the rate of those transmitters to exist out there. So in the FRB community, you might be familiar with the luminosity function. It's something similar. So we were able to kind of restrict a huge amount of parameter space. So if ETI exists, it's probably exists in this domain. Okay, and this is a very nice segue for me to kind of talk about the central part, which is the galactic center region, because the galactic center is kind of like a very exciting field to do both technosignature as well as FRBs, pulsars, all kind of science. So why were we also looking at galactic center? So in our SETI community, there is always this question that where should we point our telescope to maximize the chance of detection, right? And that particular direction is actually towards the galactic center. And reason for that is that compared to any different direction in the sky, if you look towards the galactic center, you have a high chance of encountering the largest number of stars. And that's why you have better chance of detecting extraterrestrial life. And in fact, there are a number of papers that have come out, which have in fact also highlighted the propensity metric of finding an extraterrestrial signals in the entire galactic plane, which peaks at the galactic center. So we targeted the galactic center. We actually are running this campaign for the past 5 years, which I lead, where we observe the galactic center from large number of radio telescopes, which as you can see, hundreds of hours of telescope time dedicated to it. We use Parks, we use GBT, we use SRT, and we go as high as up to 100 gigahertz. So our plan is to search from 1 to 100 gigahertz. And galactic center is as I said, has a plethora of discovery potential. Like any data we collect is not just useful for us to do detailed technosignature work, but it's also very useful for doing other science. And we've been not being shy away from that. We've been doing all kind of other science from the data we've been collecting as well. So these are a couple of papers that have come out over the years since we started surveying. Like we've been searching for pulsars. There was a graduate student who worked with me, and we did search for pulsars at C-band. There is another paper that's coming out just recently. We also looked at the galactic center magnetar. We studied it, its frequency properties. Believe it or not, we also try and search for axion, dark matter, because galactic center region is supposed suggested to have a high concentration of axion dark matter, and because of the neutron star population, they interact with it, and you have a signature of the axion dark matter at the galactic center. So we did search for that as well. We also studied the galactic center magnetar in much more finer details. So there are a plethora of different science that have come out over the years from the galactic center, because this was targeted for technosignature. But what I'm going to talk about towards the last couple of slides is some new discovery that we have made, some breaking news that I would like to share. But before I do that, let me give you some background of why is this problem kind of critical. So in the pulsar community, we've been searching for pulsars at the galactic center for the past many sort of years, or in fact more than a couple of decades now. Because the hypothesis is that the galactic center region is expected to have a large number of pulsars, large number of neutron stars. But we haven't been able to find any of them. And at least a couple of them are still, even if you kind of take the beaming geometry and everything into consideration, still you are likely to detect a few, maybe a dozen of them with the current technology, but we haven't been able to detect a single one. Why is that important? Because if you discovered a pulsar, especially a millisecond pulsar around the supermassive black hole that allows you to characterize the property of the supermassive black hole. So that's why it's very critical and very important to find pulsars at the galactic center. So we've been searching for it, as I mentioned earlier. I had a graduate student who worked with me and Akshay Suresh. We did a survey of pulsars at C-band, which is 4 to 8 gigahertz. We didn't find anything, but we were able to put a very tight constraint on existence of pulsars. This was one of the most sensitive survey for pulsars at the galactic center. So what I'm showing you in this plot, this is the period of the known pulsar. So what we did is that we took all the pulsars that we have in our Milky Way, and we moved all of them to the galactic center. So whatever is the luminosity of these pulsar, how sensitive are you in detecting those if they are at the galactic center? And different lines is actually the sensitivity curve of different surveys. And as you can see, our survey was sort of at the lowest one, so which was the most sensitive one. We didn't detect anything in that survey. We also carried out detailed searches for these pulsating signals for technosignature in a different paper, again led by Suresh, in which, as I mentioned earlier, we were looking for like a pulse radar kind of transmission. So they were not broadband signal, but using the same technique that we used to search for pulsar, now we were searching for signals that might have been produced by artificial technologies. So again, this is an example of how we can leverage the technology that we develop for pulsar searching, we can use for technosignature searches as well. But in the last few slides, I'm going to show something quite exciting. In our very, very recent survey, when we were searching for pulsars at X band, which is starting from 8 to 12 gigahertz, we have some very interesting candidate. So again, this is the same plot, different surveys, and as you can see, we were able to push the sensitivity limit down beyond what we were able to do with Suresh et al. But you might notice this red dot here, because we did detect a candidate, in fact, a millisecond pulsar candidate at the galactic center. I am not going to show too much of detail because the paper is under review right now. This is a second round of review. As you can imagine, a discovery of like this has to go through a very thorough review process, and we are kind of dealing with a referee for the past many, many months. This is second round. Hopefully it will go through. And this is the pulsar sort of folded profile. This is a waterfall plot, frequency versus pulse phase, and this is versus time. The problem with this detection is that it is extremely weak. It's close to like 3 sigma. So our chances of this being real is also is on the borderline, as you can imagine. We are at the cusp of the sensitivity threshold, so we are not 100% sure. So I did some statistical analysis of like how likely that this candidate could have been produced by just the noise. And what we found is that the chance of this produced by noise is like 1 in a million. So it is still a very strong case because of number of reasons. Number one is that we also do notice very high degree of coherent power. We also saw that the signal is more or less broadband. It is kind of appears across the entire band of observation. It doesn't last for the entire duration of observation. It kind of vanishes towards the end. But the most important thing that kind of makes us doubt this candidate is that it has not been redetected. So we've been following this pulsar for many, many years, but we haven't been able to redetect it. It was only detected once, which is unfortunate. Okay, so coming back to the wrap up of what I guess I started earlier. So technosignature and FRB and pulsar, these are all go hand in hand. Everything that we do in the technosignature field has equally kind of importance for pulsars and FRB and vice versa. This is not the end. We are kind of, as you've been hearing since morning, we are very excited for this, our new collaboration with Spotlight. We are working with NVIDIA quite closely. We have a number of dedicated GPUs and machines that we've been able to kind of get through NVIDIA. We also have this deployed system in Netherlands where we use the upper T feed. We put them on the ground and it looks at the entire sky, and we are searching for basically radio technosignature across a large area of the sky. So again, if any of you are interested to work with us, we are hiring in India. So we have a special grant that we got to work on technosignature with Spotlight. And this will be at NICER in Bhubaneswar. So if any of the students here who are just graduated, if you are interested in like a junior research fellow position, this is a paid position. So you will get stipend as well. And if you are interested in working on technosignature, let me know. But yeah, that's it. I think I'll take questions. Thank you.
Thank you, Vishal. Questions for Vishal? Vikram.
Hi, Vishal. Very nice talk. So regarding this pulsar, the last pulsar that you showed, why do you think it is, what is the reason for not detecting it again?
So in our paper, we have provided some hypothesis. There are pulsar which are called black widows, and when they are in their binary system, their emission could get obscured by the binary companion, or the geometry doesn't work out of the binary companion that might not allow you to kind of detect the pulsar. Also, that this pulsar could be in a very, very long period around the supermassive black hole, and it just happened to be at the right place at the right time when we observed. And then later on, now we probably don't ever catch it because it has gone into a very highly elliptical orbit. I mean, or it could be noise. That's again a hypothesis that we are not completely ruled out. That it is simply possible that the noise can still produce a signal like this. Chances are low, but still it is not zero.
Maybe you can look for other electromagnetic bands,
Huh?
X-rays or something, but you don't know the position.
Yeah, we don't know the position. Like, you don't have that kind of position accuracy to really look at other bands. We have tried to look at it at C band, for example. We haven't been able to detect it at C band or X band. Yeah.
Sorry, just a follow-up question on that. Was pulsar detected with some acceleration? Because
Yes.
okay.
There
And
was
was it
acceleration.
really?
It
big?
isn't high. Yeah.
Any other question? Yeah.
What is the line of sight DM of this pulsar? Is it matching?
Yes. Without sharing the exact number, it is something around 2800.
Which is matching?
Which is matching the NE 2000 model. That's why we were excited that it is indeed coming from there, not somewhere in the in the line of sight. Yeah.
And how long was the observing duration?
This was detected in 1 hour. So this is the 1 hour observation. And as you can see, like maybe towards the end, it kind of disappears. We had subsequent observations where it was not redetected. This was, unfortunately, this was the very first hour of our observation. So we don't have any data before this, so to confirm it. So look like that it was bright, if it was real, by the way. It was bright when we started observing, but then it kind of slowly got weaker towards the end, and then we never really redetected it.
Thank you.
Here's the question.
This question.
Yeah, first I missed it. At which frequency was this candidate detected?
8 to 12 gigahertz.
Okay, and so then you say it's 3 sigma. But do you see many other candidates at that level? Because the 3 sigma is very low.
Yeah.
So how do you pick this one up?
Yeah, so this is again something like corner plot, you can see. These are clusters of other candidates that we have detected. And this is actually an outlier. It is not similar to other candidates that we have detected. 3 sigma, I totally agree, it is very low. But if you look at other properties of other candidates, for example, their broadbandness, their time consistency, their time persistence, their coherent power. So if you combine all of these and take a joint probability of everything happening together, then it's very unlikely that this was just because of noise. It is not zero, but there is a small chance.
And if taking all that into account, you were to assign a new significance to it, how much would that be?
Yeah, I know. You can assign a new significant, but we are only, I'm only reporting like 3 sigma for the profile. But yeah, totally agree. Yeah.
Any other question? Jayanta.
I'm not listening.
Is there any questions? I think Ramesh, please go on.
Yeah, hi Vishal, can you hear me? Can you hear me?
We can hear you.
Oh, thanks. Thanks for the talk, Vishal. It's good to see you, at least on the screen. Yeah, so very interesting talk, and you probably partly answered my question, but I was still curious because your detection is in X band, it is 3 sigma, and did your follow-up also included with other, sensitive telescopes like Meerkat, which has now very sensitive S-band receiver?
Yeah. We are following up with the VLA right now. We have been conducting observations through VLA so far. Yeah. Meerkat, because of the we are already working with the team who is building the band 5 receiver for Meerkat. I think Ramesh, you might know them at Sardinia Radio Telescope. So we are looking forward to when that comes online, maybe next year, to kind of conduct more deep searches with band 5 with Meerkat.
Thanks. Yeah, my second quick question was for the kind of DM that you mentioned. What is the kind of scattering predicted for X band?
Scattering is a tricky thing at galactic center. If you look at the theoretical and estimate, then the galactic center magnetar itself will be heavily scattered, but we don't see that. Maybe the idea is that there is some kind of like scattering gaps in the screen that through which you are seeing the magnetar, or indeed our estimate of scattering is low. But even if you kind of so it fits if you take the galactic center magnetar scattering model. Then it fits that. So it's of the order of like a millisecond or so, and this pulsar scattering is our upper limit. Obviously, we don't have a profile to fit a scattering tail to tell exactly the scattering time scale, but it is within that limit.
Thanks. Good luck with this one.
Thank you.
Thanks, Ramesh. Any other online participants? I have one question.
Okay. Mm-hmm. Thank you for asking a techno signature question. Everybody's asking pulsar question, but it's exciting, yeah.
So what exactly the criteria you have used to mark this, and how?
So it's similar to like when you do a pulsar search, right? When you try and detect pulsar or FRB, you can put certain limits on them. Similarly, we use the same spun duct pipeline to look for these artificially dispersed signal. You see kind of like a bimodality in here. So this part of the constraint comes from nearby stars. And obviously, when you go to the galactic center, they are very far away. So the expected power that you can detect is much higher. So these constraints over here come from the galactic center region.
The sharp turnaround in the.
So that sharp turnaround is because we kind of merged the nearby star sample as well as the galactic center sample. So this turnaround over here, that's what you're referring to, that's because of the galactic center.
Well, again.